All right, so now that we've talked about WDS, let's look at the actual wavelength dispersive spectrum, so the results of WDS. So here's an example from our textbook that shows a typical spectrum. So we've got wavelength as plotted against intensity. So that's how you're going to see these plotted. But obviously there's a connection between the wavelength of an X-ray and its energy. And so you can think about its wavelength increasing from the right here over to the left, or sorry, in the opposite manner. No, I got it. Sorry about this. It's plotted a little bit unusually down here. But if you look, you'll see the wavelength is increasing from the right here over to the left, whereas the energy, which is plotted up here, is increasing from left to right. And so you'll sometimes see that they're both plotted, even though, again, the technique, the W stands for wavelength. So that's the first thing that you'll want to keep in mind. Also, you'll notice that there's multiple peaks per element. So if you look at chromium, chromium's got K alpha 1, 2, K alpha beta, and so forth. So there's multiple peaks because there can be multiple characteristic X-rays. That's something we should expect. Same thing for vanadium. We have 2 peaks for vanadium. And so that's something that can happen, is we can have a spectrum of characteristic X-rays tied to a single element. You'll also notice that of the series, the beta compared to alpha are at lower wavelengths and higher energies, right? And so that's typical of what we saw before when we looked at characteristic X-rays. And also, you'll notice here that the alpha 1, 2 typically can't be resolved, and so there's just one single peak there. So they're not so it's kind of one convoluted peak. So that's pretty common because they can't be resolved individually. Another thing that may be new and that we haven't seen before is the fact that there can be multiple wavelengths for the same characteristic X-ray line. So a good example here would be nickel. So here you see nickel K alpha, but over here, right next to it, you also see a nickel K alpha. And so if you're asking yourself, how can this happen? You got to think back to Bragg's law and remember the N in that equation. So that's the order of reflection. And so up to this point, we've only looked at first order reflections. Well, this is showing us that we have multiple orders of diffraction. And so this can be the case that we have here. But those wavelengths are going to be integer times the wavelength of another. So if we know the first order reflection, then n equal 2, right, or n equal 3, we know what those values should be based on the order of reflection. So so there's a sequence to those as well. So that can be shown. There can be some issues when integers are similar to other values. For example, cobalt K alpha is an integer value of the wavelength for sulfur K alpha. So if we have basically sulfur K alpha is equal to 3 cobalt K alpha. And so there can be issues there with the order of reflection and being able to detect other elements. So there is some overlap concern when you have these different orders of diffraction. But that's something that we can expect in these various cases.